Hi boys and girls, hi Varsha and Vidya. We come to the end of this course in this video. So last we have to discuss is a master filter receiver. So let me start with that presentation. What you will learn in this video are that you will understand the operation of a master filter receiver. Then you will derive the maximum output SNR for master filter, and then you will see a demo of a practical master receiver in Python. So this is how a baseband signal detection system will look like. I have a signal ST coming in that is corrupted by additive white Gaussian noise NT, so that RT that is equal to ST plus NT reaches my receiver filters. So it is this receiver filter that I want to design. So the output of that is a response of RT, that is ST plus NT, to this HT. Okay, let that be ZT. Now what happens is I sample at every t interval, every symbol interval, and take one value, that is the Z of capital T. Then we use some threshold comparison to get a value of the bit received. You make a decision approximation of the bit that is transmitted. Now it is to be proved that this HT should be matched with my ST. That is the concept of a matched filter. Now let the response of the filter to the signal. What is coming to this HT? This is my receiver filter. This is what I am trying to design. Now let us consider separately. There is a signal coming and a noise coming. So what this matched filter is an optimal filter. So what it optimizes is that it maximizes the output signal to noise ratio. Earlier you have seen a correlation receiver where it is also an optimum receiver. What it optimizes is that it minimizes the probability of error. Here in the case of a matched filter receiver, that maximizes the output signal to noise ratio. So I have to compute the output signal to noise ratio and see for what value of HT or HF this output SNR is a maximum. So let us see the response of the filter to the signal as well as the noise. So let the response of the filter to the signal ST be say 80. That is, if I put in the frequency domain, AF is equal to HF times SF, because this is a system response. You know this from your signal sense system course. Now, what is the time domain representation of that? I take the Fourier transform of Fourier inverse transform of this 8AF. So it is minus infinity to infinity HF SF e raised to j2 pi ft df. And I do a sampling at t equal to capital T, so that this A of t, I marked in the diagram, I marked as Z, I marked it here 80 or ZT, whatever it is. A capital T, that is equal to minus infinity to infinity HF SF e raised to j2 pi capital F capital T df. Now this is a single value. This AT is a single value. Okay, the value of A small t at capital T is a single value. Now this is my output signal value. So square of that will be my output signal power. Now I have to compute the output noise power. So what is I assume that the incoming signal is AWGN with say the power spectral density be eta by 2. So the output noise power will be eta by 2 minus infinity to infinity mod HF square df. HF is your master filter transfer function. So mod HF square df. So what I will do is, if I take I know the output signal value and output noise power, so I can compute the output SNR as this. This AT is a single value, so power of that is just the square of that. Mod AT square will be the square of the output. This will be the output signal power. That divided by N0 is your output noise power. So the signal noise ratio at the output is, what is A capital T? It is minus infinity to infinity HF SF e raised to j2 pi ft df mod square. And divided by what is N0? We previously found out that it is eta by 2 sigma mod HF square df. Now this equation, this value, that fraction can be simplified if we use something called the Cbs inequality, Cauchy-Schwarz-Bunyan-Cauchy inequality, which says that you know that modulus of an integral is less than or equal to modulus of this mod x1f x2f df whole square, this is less than or equal to integral of mod x1f square df integral x2f df whole square. There's an inequality like this. Even by even if you don't know the proof of that, you can easily understand by experience, because this integral value is taken mod and square, because this can even be negative. So this value should be less than the integral like x1f x2f square, because x1f is always a positive, mod x1f is positive, and mod x1f square is a positive value. So these two are positive values. So when we take this product, this must be greater than this, because x1f x2f can be smaller than this. And when you take the integral, this mod square will be less than this. This is a Cbs inequality. So I can use that inequality here to understand, to split this numerator part. So, and the equality happens when one is scaled conjugate of the other. Like if equality happens when x1f is equal to k times x2 conjugate f, okay, with some constant k. So that by this equation, by my earlier inequality, integral minus infinity to infinity, this is my numerator part of my signal noise ratio, that is h of s of e raised to j2 pi ft df whole square. This is less than or equal to, take them individually, mod h of square df into mod s of square e raised to j2 pi ft whole square. Okay, and this e raised to j2 pi ft mod is a 1, because this magnitude is a 1, so that the left side is less than or equal to minus infinity to infinity mod h of square df into minus infinity to infinity mod s of square df. So if I use this in the previous equation here, instead of that equality, I can write s by n less than or equal to this right part, that is mod h of square df into minus infinity to infinity mod s of square df divided by eta by 2. This is my output noise power integral h of square df. Now I can cancel off one integral, this mod h of square df I can cancel off, so that this s by n output is less than or equal to 2 by eta into minus infinity to infinity mod s of square df. And the equality, so that the maximum value of the output signal noise ratio is nothing but 2 by eta minus infinity to infinity mod s of square. When does this equality happens? When one is a scaled conjugate of the other. So that the maximum SNR happens when hf is equal to s conjugate f e raised to minus j2 pi ft. If I take the inverse transform of this equation, I easily deduce that ht is equal to st minus t, meaning that my filter ht should be matched with my input signal st, or input filter. This actually, some impulses are coming to an input filter, and this st is generated, you know. You learned it in the ISI, model of ISI, and all you have seen this anyway. This transmitter filter, this receiver filter should be matched to the input filter, or your transmitter filter, with some inversion and delay. So the last equation means that the maximum output SNR, for maximum output SNR, the receiver filter should be matched to the input signal, and that's why the name, the matched filter. So let us see one example. Say if suppose your incoming signal is of this shape, say st is this shape, then my ht, what should be my ht? Should be st minus t. You know that s minus t will look like this. Okay, st minus t, s minus t will look like this. What is my receiver filter? How can I receive properly if my ht is st minus t, so that this is moved over here. So this is flipped in time and then translated by t units, so that it comes something like this. So if you have a filter like this, you can easily receive these signals correctly. That's the idea of a matched filter. Now let us look at a practical matched filter. Let us look at something with RRC filter, or root raised cosine filter. I told you in the previous discussion of the ISI that the with the root raised cosine filter, you have very little ISI. So I assume that I use a look at this block diagram. I use a rule-wise cosine filter here. So here I use a random binary stream, some maybe some 5,000 or 10,000 values I create. Then I upsample by 4 because if I don't upsample, the convolution will not be correct, because this is to be put into a pulse shape, say Pn, let that be Pt or Pn. This is my transmitter filter Pn, and so for that convolution to happen correctly, there should be sufficient number of zeros between each random bit. So that what is an upsample by 4? That means I put 3 zeros in between every binary value. After every binary value, I put 3 zeros. So that's an upsampling process. Then I convolve with some pulse shape PNI. Here I say that PT is this. This is my root raised cosine pulse. You saw this in the ISI topics. You saw this. Then this is passed through an additive white Gaussian noise channel, and this is given to a GN. GN is nothing but a version of PN. It is same as PN because this PN PT is a symmetrical function. So and it's a real value. So even if you take a conjugate, nothing happens, and even if you flip it, nothing happens. If you flip it in time, nothing happens, because this is a symmetric function. So when you run this simulation, you will understand this. So here Pn and Gn should be the same. Why it is same? Why it is not a conjugate? Because this Pt is a real value. So conjugate is the same, and it's a symmetric function. So flipping in time does not change anything. So this here, when I use this Pt, Pn and Gn should be the same. Then I sample at every symbol rate, and then some decision is made. Okay, whether it is positive or negative, depending on that you receive these bits. Then you compute the Bitterrate for different signal to noise ratio, and plot the Bitterrate versus the signal to noise ratio, and you can appreciate that. Now let me run that simulation. Let us come here. I will show you a code. So I import the SciPy and PyLab modules. Then I write a function for upsampling. Okay, it's a simple function for upsampling. All I need is I put n zeros after every bit. I put n zeros and return the upsampled value. There is nothing very fanciful about that. Now I generate a random binary stream. Say here I generate some 2000 values. Okay, then I upsample by 4, so that upsample by 4, that is UPB is an upsampling by 4. Now I have to create a raised cosine pulse for my PN. Okay, I have to create this PN. PN is created by this. Let TB1 and alpha is a 0.3. That parameter for your alpha. Here, if you come here, this is an equation. So there's a parameter alpha and T here, capital T here. So this is what I'm trying to create here. So these are for the sake of computation, I put them into different functions, and I realize this is my input function G, the input filter G, and your upsampled signal is now convolved with this to create the transmitted signal Y. This is my transmitted signal. Y is my transmitted signal. It's a convolution between the upsampled version of my bits and my root raised cosine pulse. Now, as usual, I create some noise, like SNR I put from minus 40 dB to some 5 dB with an increment of 0.5 dB, so that my S is 10 raised to minus 0.1 BR. And then I initialize a blank bit error array. Then for different power values, I create noise signals, additive white Gaussian noise, and I add this noise to my transmitted signal Y. Okay, and this is the one that is coming to my receiver. Now, what is my receiver? It should be the same as my transmitter, because I used a root raised cosine pulse. It is symmetric and real, so that this is my actual receiver. Here also I convolved with G. Okay, then I take the sign of Z1, and then I check for different. I remove the convolution tails. Okay, because when I convolve with a G, some convolution tails do happen. I don't want that to happen. So what I do is I cut off the convolution tails. Okay, these are ln G to ln G plus 1, so that I remove the cut off the convolution tails. Then I take every fourth value because I have to downsample this. So I have to take the every fourth sample. Then this is my actual received signal. So the sign is my nothing but my what is this? This is my thresholding. Okay, the sign is my thresholding. It is positive. It's a +1. If it's a negative, it is a 0. Okay. So this ln to ln this thing minus ln g means I am removing the convolution tails, and east to 4 means I am removing the upsampling. Okay, I am downsampling by 4. Then I compute the difference between Z3 and my original bit B. What is my transmitted bits are my B. B is my transmitted bit. So I take the received signal and the received bit, and I take the difference between that, and I compute the total number of errors. Okay, divided by the total length of the bits. Okay, so that then this is my bit error, and to this earlier BER array I append this in every iteration, that is for every noise variance or every noise variance I append this value. Then I first I plot my RRC pulse, then I plot my transmitted signal. This is my RRC pulse, this is my RRC pulse, this is my transmitter and receiver filter. Then I plot my transmitted signal Y. Then I plot the semi-log plot, I plot the Bitterrate against SNR. Now let me run this code. You can appreciate this. This is where I am sitting. So I turn on this, I type Python, and I increase it slightly so that you can all see this. Now I run this match code, run match. You also please run these codes and type up these codes and run them and appreciate that. So you can see that this is my transmitter filter, this is my root raised cosine pulse, this is my transmitter filter, and my upsampled thing is upsampled bits are convolved with this RRC pulse, so that the transmitted signal looks like this. I will zoom it slightly, and you can appreciate that. Okay, I will zoom it again so that you can see that these pulses get repeated for every 1 or -1. Okay, you see why I did upsampling. Otherwise, this convolution will not happen this way. This convolution will not result in sequence of pulses. Okay. So this is how the transmitted signal looks like. This is added with white noise, and then try to receive. So how they are received, I can understand only with the help of the Bitterrate SNR curve. So that comes this way. If I close this, I can have the, you can see the Bitterrate SNR curve. For small, for low SNR, say -40 dB, etc. This so this is around 0.4 here. This is around 0.4, slightly around 0.5 something. It is it is around 0.49 at deep noise. It's around -40 dB SNR. It's a very poor SNR. So if you come to -20 etc., this comes to around 0.3. Okay, and when it comes to say 0 dB. When it comes to 0 dB, you can see that this is some 0.2. The Bitterrate is 0.2, and as the signal noise ratio improves, this BER Bitterrates comes down. Bitterrates becomes very small. Okay, this is also very similar to your Q function you have seen in BPSK and the like. Okay, this is how the Bitterrate SNR curve for a matched filter looks like. Okay. You may type up this code, and you may run the simulations and appreciate that. You please understand why I need an upsampling, what's the role of the root raised cosine filter, how this is realized. Now let me go back to my presentation. This is a BER-SNR curve for the matched filter. This is very important. You should be able to draw this curve. And what you understood in this is video session is that you understood the operation of matched filter receiver. Then you derived and understood the maximum output SNR for matched filter. and you observed the demo of a practical matched filter in Python. So with this presentation, we are coming to the end of this course, EC 301 digital communication, and half of this is done online and with the help of videos due to the COVID situation. And you learn with the help of this, and I wish you best of luck in this course. And I will post 2-3 problems from matched filter that is available in analog and digital communication by Sue. Okay, so you can do this. You learn with the help of these videos, and you do well in the upcoming exams. I thank you all.